Okay, Algebra 2, we're going to move into section 6.3. The title of this is Binomial Radical Expressions, and what I hope everybody realizes real quick before we move on is that two of those words are what we've been dealing with for all of chapter 6 so far, radical and expressions. The new word here today is binomial. So if you think real hard about this, a binomial, of course, means an expression that has two terms in it. That would tell you that everything we've been doing up until this point has been simpler than that. It's been a monomial radical expression. So the rules for binomial radical expressions are a little bit more complicated, but the same basic concepts remain. So let's take a look at what our big key concept for the day here is. That you can take this little expression right here, a multiplied by the nth root of m, and you can add that to b multiplied by the nth root of m also, and get a result that we'll talk about in just a second. I do want to point out that for the very first time in chapter 6, we're now talking about an addition expression, and of course there'll be subtraction in here as well. That's what makes these things binomials. Binomials have two terms, and terms are separated by pluses and minuses. So this is the first time we're talking about addition. Now, if we go through a little bit of vocab right here, what I want you to notice is that these two monomials that are being added together are both radical expressions, and they have the same index. These are both nth roots in what I've written right here, and that's similar to what we were doing when we were multiplying in section 6.1 and 6.2. However, what's new here is that the radicands have to be exactly the same as well in order for those two terms to be added together. So you can add the nth root of m plus another nth root of m, even if, and the word here is coefficients, the number out in front of the radical that's being multiplied. Even if the coefficients are different, you can add together two radicals if their indices are the same and if their radicands are the same. And so this is how you can put them together. Now, really, what I want you guys to notice is an nth root of m added to another nth root of m is going to get us, you guessed it, an nth root of m at the end. And the new coefficient out in front is just the sum of the previous two coefficients. Okay, so that's a whole lot of arrows and circles that I just did right there. So let me get rid of all that. But what's kind of important is what's written right down here, guys. And I don't necessarily think you have to write this in your notes, but I at least want to talk about it. If the indices or the radicands are not equal to each other, then the expression cannot be simplified. But again, if the indices and radicands are the same, like the nth root of m and the nth root of m, then yes, they can be combined and added together. Now, I would expect most of you would look at all this garbage and all these letters and all these fancy words and say, I don't get it. Well, let me show you an example right here that hopefully is going to make things a little bit easier to understand here. So, part 2 of our notes, we're going to talk about adding and subtracting radical expressions. And here we go. 6 times the cube root of 5 plus 7 times the cube root of 5. So the first question you would want to ask yourself, I suppose before doing anything else right here, is can we evaluate or simplify either of those expressions just the way that they're listed? And the answer to that is no. 5 is not a perfect cube. And furthermore, there aren't any perfect cube factors that divide evenly into 5 other than 1. So you can't simplify them the way they're written. The next question would be, basically, are they like terms? Like, for example, down at the bottom of the page, if I wrote 6x plus 7x, and I gave you the directions to simplify, every Algebra 2 student would not spend more than about 2 seconds thinking about this problem and say, oh yeah, the answer is 13x. Now, what we do there in red for adding like terms is exactly what we're going to do the same thing as right here on the top. These two terms, they don't have the same variable, but they do have the same common factor. This is 6 multiplied by the cube root of 5 plus 7 multiplied by the cube root of 5. So all you have to do now, according to this rule that we just wrote down here, since the indices and the radicands are the same, we can combine these two terms. We put the 6 and the 7 together to get a 13, and then just like here, the x and the x just made 13 x, but the common variable, the common factor didn't change, the same thing happens right here. This is 13 multiplied by the cube root of 5, and there is not a darn thing you can do to simplify that expression any further. There's no perfect cube you can divide out from 5, and that's it, guys. You just end up with 13 times the cube root of 5. So there will be a few problems, not very many, where all you're really doing is combining like terms, just like you learned how to do in pre-algebra or algebra 1 when the common factor was a variable, like an x. Here the same thing happens in this section, except now the common factor is a radical. But as long as it's the same, in this case the cube root of 5, your two terms are able to be combined, and you end up with that same common factor, in this case the cube root of 5, in your answer. But as I said, not many of your problems are going to look like that. This is a little bit more like what you're going to see. 5 times the fourth root of 405, and then minus 3 times the fourth root of 80. Now, unlike the problem that we just did, these two radicands, quite obviously, are different from one another. So it's going to be really tempting for you guys to look at a problem like this and say, oh, there's nothing we can do, so let's just circle it and move on. Well, you're missing most of the point of a problem like this if that's what you do, and guess what? You're going to miss most of the points, or all of the points really, if that's what you do on a quiz or a test question. Before you're ready to give up on a problem and say, I can't go any further, you have to stop to think about whether or not those radicals can be simplified before you do anything else. So, you probably have a table of perfect squares and cubes and fourths and fifths in front of you right now. The first question you should ask yourself is 405 a perfect fourth? So if you look in your x to the fourth or your fourth root columns right there, you're going to find that no, that's not the case. But the question now becomes more interesting when you say, is there a perfect fourth that divides evenly into 405? So the first thing I would do is take half of 405, which is what? I multiplied instead of divided, 202.5, okay? And then start looking for perfect fourths that are smaller than that. And if I'm not mistaken, the one you're going to find is that 405 divides evenly by 81, which is a perfect fourth. So I'm going to break up that 405 into an 81 times 5. And on the next part of this problem, minus 3 times, here we go, we're going to look for a perfect fourth now that divides into 80. And there, the one that you're going to find is 16. So that 80 becomes 16 times 5. And just like we were doing back in section 6.1, we circle, in this case, our perfect fourths. And we take the fourth root of each of those numbers. So I'll go step by step right here. This is going to be 5 times the fourth root of 81 is going to be a 3. And then you can't do anything with this 5 right here, so you're left with the fourth root of 5, and that has to just stay there. Minus, here we've got a 3 times, and then right here, the fourth root of 16 is going to become 2, but you can't do anything with that, so that's times the fourth root of 5. So we multiply the 5 and the 3 to get a 15 times the fourth root of 5, minus 3 times 2 is going to give us a 6 times the fourth root of 5. And hey, will you look at that? By total dumb luck, in no way did I plan this, you now have two radical monomials that are being subtracted, which makes it a radical binomial, and they've got a common factor of the fourth root of 5. So we'll just subtract the coefficients here. We'll do 15 minus 6 to make 9. And then the common factor of the fourth root of 5 just tags along for the ride. Before you box it up, you probably just want to ask yourself right there, can I simplify the fourth root of 5? And the answer to that is no. So that is your final answer. Now, one thing I just want to make sure that everybody understands that we're doing, and this is kind of a way you guys can check your work on a quiz or a test to find out if you're right. We're going to take just a second right here, and I'm going to type in the original expression, just the way it's written right up here, into my calculator. So do this with me here, guys. 5 times the fourth root of 405. So 5 times, let's see, my calculator is a little different than yours, but the fourth root of 405, right arrow to get out of that radicand, and then minus, and what came next was 3 times the fourth root of 80. So 3 times, and then here we go, the fourth root of 80. Now, I'm pretty sure, everybody, this is going to end up being an irrational answer. Yeah, I get this really ugly decimal right here of 13.458, blah, blah, blah. That really doesn't tell me that I'm doing this problem right or wrong. But what I'm now going to do is type in my answer here, 9 multiplied by the fourth root of 5. And what we get from this answer, as far as the calculator's decimal approximation, is going to tell us if we're doing this problem right or not. So let's type in 9 times the fourth root of 5. And again, I'm going to ask this calculator to round for me. And you'll notice, guys, and hopefully you got the same thing, we got the exact same ugly, irrational decimal answer twice. Now, if you take a look at what I have on the left side of my screen right now, I've got two different expressions right here, and pretty clearly the first one, this one right here, is more complicated than the second one right over here. That is because we have simplified the expression. But the important thing is that when you look at their decimal equivalents, there's one of them, and here was the first one, they are exactly the same. Guys, we did not change the value of the expression. This expression that we started with right here gets you the exact same value as this final answer, but we found a much simpler way of expressing that ugly number. And so when the directions tell you to simplify in a problem right here, you better make sure, if I had time at the end of a quiz or a test, this is what I would do, that this decimal value and this decimal value here at the end are exactly the same every step along the way. If they're not, if you somehow change the value of it, that is a guarantee that you did something wrong because you're never allowed to change the value of an expression. Okay, on to a third problem, and this one I think you're going to see quite a bit of on homework as well. The square root of 12 plus the square root of 75 minus the square root of 3. Now again, you're probably tempted at first to look at this and say, can't do it because the radicands are all different. Well, we got to dig a little bit deeper. We're talking square roots right here. So what perfect square divides evenly into 12? That's going to be a 4, and it goes in there 3 times. Plus, what perfect square divides evenly into 75? That's going to be a 25 times 3. And then there is no perfect square other than 1 that divides evenly into 3, so that just remains the square root of 3. I like to circle my perfect squares now, which are 4 and 25, and that's it, and then bring out not the number itself, but the square root of that number. So the square root of 4 is 2, and that gets multiplied by a root 3. Plus, the square root of 25 is 5. That gets multiplied by a root 3. And you can't do anything with that last term there, so minus root 3. And now, just like in the last problem, we had to do a little bit of digging, but it now seems that every one of those radicands is the same, and every one of those indices is the same. Remember, guys, that a square root is an index of 2. That means that these three terms can be combined. So let's just put our coefficients together. 2 plus 5 makes 7, minus a 1 right here, everybody, is going to get you a 6, and then the root 3 just stays, and we end up with 6 times the square root of 3. Now, one thing I want to show real quick, no need for you guys to change this in your notes right here, but real quick, what if? I made the problem a little bit different, and instead of that last term being a square root of 3, let's say it was a square root of 13. So now in the next line, we said, all right, is there a perfect square that divides evenly into, in this case, 13? The answer is still no. You can't do anything with that, so it's just the square root of 13, which means now that remains the square root of 13. And what does that do for our final answer? That changes some things. Now, these two terms can be added together, combined, I should say, but this one cannot. So if you ever saw a problem like this, you'd add up the ones that do have a common factor. 2 root 3 and 5 root 3 is going to be 7 root 3. And then that minus root 13 just gets tacked on at the end right there, guys. And since you can't simplify either one of these radicals any further, and they don't have the same radicand, that would be your final answer at the end of this problem here. So if I'm remembering right, I think a decent number of problems on your homework kind of have you end up with, I should say here, with two different radicands. out of maybe 3 or 4 terms, so it is possible then that your answer would be a binomial as well. So just be on your toes, guys, and don't be shocked if that happens. But I should go back and not change. There you go. That's what this problem looked like. Okay, guys, those were 3 examples of adding and subtracting radicals that I wanted to do with you. Now we're going to shift gears a little bit and we're going to talk about multiplying radicals. And I'm not really going to write any rules or key concepts right here because these use the rules that we've already talked about in 6.1 and specifically 6.2. All you need to remember here, guys, to know how to do a problem like this is that, well, for example, right here, 3 root 2 is a monomial. Okay, and that's being multiplied right now by 3 minus 5 root 2, which is a binomial. And what I'm about to tell you has been true since, I don't know, probably about 7th grade math for you guys. If you want to multiply a monomial times a binomial, that's what the distributive property is for. It's funny, almost every math student worth their salt knows the distributive property, and if you give them a problem like 5 times 7x minus 2, every single one is going to know to distribute that. But if you ask them, hey, when do you use the distributive property? Not that many people can come up with the right answer. The distributive property is a monomial times, well, really, any polynomial. So what are we going to do here, guys? We're going to start off by multiplying 3 root 2 times 3. Well, the coefficients are 3 and 3. We're going to multiply those together to get a 9. And then we would multiply the radicals together, but this term doesn't have a radical. So root 2 times nothing is just going to be root 2. So 3 root 2 times 3 just gets us this 9 root 2. And then minus. All right, let's multiply now. Let me switch back to purple right here. Let me multiply now. 3 root 2. Gotcha. Multiplied by 5 root 2. The 3 times the 5 is going to get us a 15 right there. And I want to show you guys what I think is a more efficient way to handle what comes next. Root 2 times root 2. Most Algebra 2 students want to put those together and make a root 4. And that is not wrong, everybody. 100% right. The only thing is, this now gets a little bit tedious because on the next line down, you've got to simplify that root 4 to a 2 and eventually then make that a 30. That's where we're going here in just a moment. But what I would really like you guys to start thinking about and to start saying is that root 2 multiplied by root 2, yes, it becomes root 4, but that just becomes 2. Root 2 times root 2 is 2. It's not wrong to say that it's square root of 4, but it's faster to do it this way. So what are we doing now, guys? You can't do anything with 9 root 2 minus, and 15 times 2 is 30. Guys, that's it. There is nothing else you can do to combine terms right here, to simplify radicals. That's it. That's your answer here for how to multiply 3 root 2 times 3 minus 5 root 2. We end up with a 9 root 2 minus 30, and it doesn't get any simpler than that. So that's an example of how to do a monomial times a binomial. It's just going to be the distributive property. But now, the plot thickens a little bit as we look at example B. Now we are multiplying a binomial. In fact, let's write this out. A binomial multiplied by, and what do we have here? Another binomial. And as I'm hoping you guys know by now, the way we multiply a binomial times binomial is by using FOIL. First, outer, inner, last. We've been doing this, guys, since chapter 4 here this year. So it's literally been months. And this is something you guys learned back in Algebra 1, if not before that. So let's get to it. First product, 9 times 9 is going to get us 81. I'm going to go one at a time here. The O is the outer product, which is this times this. So 9 is going to get multiplied by a positive 5 root 6. That's going to be a plus. 9 times 5 is 45, and then a root 6 just tags on at the end of that. The I of FOIL stands for the inner product. What did I just do? Which is this term right here times this term, that times that. Now that is a negative, and then again, 5 times 9 is 45, and a root 6 just goes along for the ride. And the L of FOIL is the last product. This term right here, negative 5 root 6, times a positive 5 root 6. Well, a negative times a positive is negative. 5 times 5 is 25, and root 6 times root 6 is just 6. You can write it as the square root of 36 if you want, but that's just something you're going to have to clean up on the next step. Now, we're not quite done yet. As is often the case, most of the time when you do FOIL, the outer and the inner products end up being like terms and can normally be combined. And as you'll notice, and I bet some of you saw this already and are not surprised, these two terms are opposites of one another. Positive 45 root 6, minus 45 root 6. And in a case like that, they simply wipe each other out. So we end up now with an 81 minus, and 25 times 6 is 150. And I just want to make sure I get this right here. 81 minus 150 is going to give us a negative 69 for our answer right there. Now, what I wanted everybody to notice and to take away from this problem is I said, okay, this is binomial times binomial, which is when we do FOIL. And that was true. But these were not random binomials. These were two conjugate binomials. And that's a phrase I've been using all year long, but most Algebra 2 students choose to ignore me and fight that right there and don't learn what that phrase means. So maybe now, for the third or fourth time we're seeing it, maybe it'll sink in. These two binomials are conjugates because their first terms, 9 and 9, are exactly the same. But their second terms, everybody, negative 5 root 6, positive 5 root 6, their second terms are opposites of one another. And every time you FOIL two conjugate binomials, you end up then with a binomial expression as opposed to a trinomial. Like, for example, if I gave you x plus 8 times x minus 8, you would do FOIL here and get x squared. The outer product would be a minus 8x. The inner product would be a plus 8x. And the last product would be a minus 64. And again, the outer and inner products just cancel each other out, and this is when you end up with a binomial, x squared minus 64, and that's as far as you can go. Now, if I had changed that 8 to a 7, these two terms are not going to cancel out, and we would end up with a linear term in the middle here. So that's just kind of a refresher about what happens when you FOIL two conjugate binomials. Now, what's weird about this one, yeah, I was expecting those two middle terms to drop out, and I'd be expecting a binomial expression, but these are both real and rational numbers, so they can just be combined. So the real takeaway from this problem is that when you multiply two conjugate binomials with irrational numbers, you end up then with an answer that is purely rational. There is no square root within this answer, and that's going to become important in about 3 minutes. Okay. Those are two examples that deal with multiplying radical expressions. Let's take a look at a dividing problem. And I'm starting you with this one, but now that I look at it, I probably don't need to, because this is something we did already in 6.2. So if you guys want to skip this, that's fine. But we've already talked about how to divide with radical monomials right here. So how would I do this? The first thing I would notice is that 15 and 3 can be divided. So I'd probably rewrite this as, now I can't do anything with 5 over 2. So I'm still going to have a fraction here with a 5 on the top and a 2 on the bottom. But as far as the radicands, 15 divided by 3 is going to make that 5 root 5 over 2. And actually, now that I look at that, this problem is done. All right, I could have multiplied both sides by root 3. That's where I thought I was going with this, and we would have gotten a 5 root 45. 2 times root 3 times root 3, that's 2 times 3, which is 6. Then we would simplify the 45 into 9 times 5. The square root of 9 is 3 times 15, or times 5 is 15, root 5 over 6. And then you would divide a 3 out from both the 15 and the 6 and get 5 root 5 over 2, which is exactly where I was a second ago. All right, the first way I did that was easier. Let's forget that problem. This is the one that's new and interesting for you guys. How do you do division with irrationals, with radicals, if there's a binomial involved? Well, The key to this, everybody, is that much like we did at the end of 6.2, we're not allowed to leave a radical in the denominator. And the way we're going to get around that, I'm going to go back 2 slides here, everybody, to example 3b and talk about what we learned here. When you multiply 2 conjugate binomials, your outer and inner products will cancel each other out, and it will get you a purely rational number. So, right here, we need to find a way to turn that denominator rational. So the way we're going to do that is by multiplying both the top and the bottom of this fraction by the conjugate of the denominator. Conjugates have the same first term, so it'll start with a 4, but the second term needs to change sign. In black, it was a minus 2 root 5. This is now going to become plus 2 root 5. That should do what we needed to do in the denominator. Now in the numerator, you're going to do the exact same thing. 4 plus 2 root 5 is going to get multiplied there as well. Now the order in which you do this doesn't really matter. I'm going to do my denominator first, just so you guys can hopefully understand, if you don't already, why we did what we're doing here. We have a binomial times another binomial, so we're going to do FOIL. First product, 4 times 4 is going to get us 16. Outer product, here and here, 4 times a positive 2 root 5 is plus 8 root 5. Inner product then, this times this, that's negative 2 root 5 times 4 minus 8 root 5. And then the last product, it's negative 2 root 5 times positive 2 root 5. Negative times positive is negative. 2 times 2 out in front is 4. And then root 5 times root 5 just becomes 5. All right, so what I'm hoping you see here, the outer product and the inner product are opposites. They're going to cancel each other out on my next step, and I've got a little simplification left to do right there. Let's go to the numerator now. Now this is just straight up FOIL, guys. It's a binomial times a binomial, but these are not conjugates. So I'm expecting 3 terms here and not 2, but let's check it. First product is 7 times 4, which is going to be 28. Outer product, which is this, 7 times 2 root 5, is a plus 14 root 5. Inner product is right here, root 5 times 4, so that's plus a 4 root 5. And then your last product is this guy multiplied by this guy. So positive times positive is positive. There's a 2 there, and then root 5 times root 5 is just 5. Okay. So that takes care of the second step. Now in the third step, let's see what we can actually put together right here, guys. I think we can probably do a couple of things at once. No, I'm going to go slow. Up in the numerator, I see a 28 right there. I've got a plus 14 root 5 and a plus 4 root 5. Those are like terms as well. So plus an 18 root 5. And then at the end of that, we've got a plus 10. Down in the denominator, I've got a 16 right there. These terms cancel each other out, followed by a minus 20 at the end of all of that. All right, guys, give me just a second right here. Okay, back to that, and we're in business now. Okay, in the numerator, we did get a trinomial like I expected, but the first and the last terms are alike. They can be combined. 28 and 10 is going to be a 38. Now you just do plus 18 root 5. Those are not like terms. They can't be combined. Down in the denominator, though, you can do something. 16 minus 20 is negative 4. And in a lot of cases, you'll be done at this point here. But what you want to check is you've got 3 numbers here, 38 and 18 in the numerator, and then this 4 in the denominator. And if they all have a common factor, we need to divide that out. Well, it's not much, but I think you can take out a 2 from each one of those. So dividing by 2, the 38 becomes a 19, plus 18 divided by 2 is going to be 9. You do not do anything to your radicand, everybody. That remains a 5 there. And then dividing by 2, that negative 4 becomes a negative 2 down on the bottom, and that is as good as this thing can get, everybody. So that's our final answer right here for problem, what was that? 4B. That's what we got there. 19 plus 9 root 5 all over -2. All right, guys, that's everything I have for you from section 6.3. Hopefully not too bad of a section. So go ahead and dive into that homework and let us know if you have any questions. Good luck, guys.